So I'm gonna turn on now on my video, and then I'll listen to it, and then we'll follow it. Okay, just turn on now. So this.
The cells consist of ceramics. Ceramic powder is mixed with a number of other components in ball mills to get a uniform thick paste. The paste is cast in long, thin sheets, which are only 1/4 of a millimeter thick. These sheets eventually provide the high mechanical strength of the cells. Subsequently, the active anode and the SOFC electrolyte are applied by use of spraying. The cells are then cut to the desired size and fired at a high temperature in order to sinter the ceramic particles together. Finally, the cells are tested for gas leaks. The cathode layer is applied to the gas-tight cells, and then the cells are sintered again at a high temperature. Subsequently, a contact layer is applied. This ensures electrical contact between the cells. This layer is printed onto the cells like a screen print. The fuel cells are then cut to the final size by use of an advanced laser cutting technique, and then they are ready for use. At Topsoe Fuel Cell, the cells are stacked alternately with metallic interconnects. 50 to 75 cells and a corresponding number of interconnects are required to get a fuel cell stack with an electrical output of 1 kilowatt. Pipes for supply of fuel and air and pipes for removal of water and CO2 are mounted on the stack together with 2 power outlets.
This section, just pause the video, please, just for me to go through this point. What happens is that the fuel cells, they are stacked because each fuel cell has only a limited voltage. In order to reach 1 kilowatt of voltage, it needs around 100 cells. So this means that each cell has around 0.1 volts. No, around 1 volt. Each cell has 1 volt. You stack 100 cells, you'll have 100 volts for each cell. So the cell has a limit, and I'm going to talk about this, why each cell has a limit of voltage. But if you connect one cell to the other with a electric connector, with a layer that conducts electricity, you stack them one over the other. What happens that their voltage in series, they multiply, they sum 1 by 1 by 1 by 1, and then increases while it goes up the number of cells. So let's go back to the video.
After assembly of the stack, its components are activated at a high temperature. Now the stack is finished. It is then tested to confirm performance before it is shipped to a customer or used for research and development purposes at Topsoe Fuel Cell. It is not possible with the naked eye to see how a fuel cell stack produces power. However, this little test shows the working principle. When the fuel cell is heated to a high temperature in a gas flame, it uses the non-combusted gases in the center of the flame as fuel and starts producing electricity, which makes the propeller rotate. SOFC fuel cells can be applied for power and heat production for residential homes, where they would substitute the traditional natural gas or oil-fired boiler. The family consumes most energy in the morning and in the evening when they're at home. An average Danish family with 2 adults and 2 children consumes yearly about 25,000 kilowatts of electricity and heat. With the Danish utility prices, this corresponds to an annual expense of about €3,100. An SOFC fuel cell is an environmentally friendly alternative to a natural gas or oil-fired boiler. SOFC fuel cells will run on natural gas, gasified biomass or other fuels. The fuel cell converts the fuel to electricity and heat, which are both used in the house. An SOFC fuel cell is very energy efficient and environmentally friendly. The heart in the SOFC fuel cell is the fuel cell stack. This consists of 50 to 100 ceramic fuel cells, which are stacked on top of each other. Each cell is only 1/3 of a millimeter thick. Metallic interconnects are placed between each cell to ensure electric contact between the cells and to distribute air and fuel to all cells. During the night, no or only little electricity is used. However, the fuel cell keeps running and provides heat for the family. The power which is produced and not used by the family is exported to the central power grid. The family is paid for the energy it is exporting to the electricity grid. In the future, the family will hopefully receive a very good compensation since the electricity is produced in an environmentally friendly way. SOFC fuel cells is an environmentally friendly and energy efficient way to produce electricity and heat for private homes. This is due to the high efficiency of the fuel cells and because no energy is lost in the power grid and central heating pipes between the power plant and the home. By use of SOFC fuel cells, an average family can save about €350 per year on its expenses for electricity and heat. For gas stations, data warehouses, hotels, hospitals and supermarkets, it is important to have a reliable power supply all the time. With an SOFC fuel cell, power outages can be prevented. SOFC fuel cells produce power from natural gas, gasified biomass and other types of fuel. This means that it can work independently of the central power grid. By having an SOFC fuel cell supply the power, the supermarket can prevent its food from going bad in case fridges and freezers are without power. Hotels and gas stations will not have to cease operating because the computers and the cash register are without power. In addition to the high reliability, SOFC fuel cell is an energy efficient and environmentally friendly technology for the production of electricity. SOFC fuel cells have great advantages if used as electricity supply for trucks. During long hauls, the driver must stop to rest. And then he makes use of the truck's many facilities: TV, computer, coffee maker, air conditioning and other appliances. Sometimes it is also required to keep the cargo cold. All these uses demand power in excess of what the battery can supply. The consequence is that many trucks idle and let the truck's diesel engine supply the power via the generator. Idling diesel engines are a source of massive air pollution in North America and in Europe. In the US alone, 3.8 billion liters of diesel is yearly consumed by idling trucks. With the same amount of diesel, a truck could run 11 billion kilometers or 250,000 times around the Earth. At the same time, 11 billion tons of CO2 and 180,000 tons of nitrogen oxides are emitted. This is about 10 times the CO2 emission of a medium-sized coal-based power plant. A solution to this massive environmental problem is to equip the trucks with an SOFC fuel cell. When the truck is standing still for long periods, the engine is turned off and the fuel cell is started. The fuel cell converts diesel to power, and this conversion is much more efficient than with the diesel engine. If all large trucks in the US used SOFC fuel cells instead of letting their engine idle, 2.5 billion liters of diesel could be saved annually. At the same time, the polluting emissions would be reduced by 2/3. To understand how a fuel cell works, you have to look inside the cell. The fuel cell combines three separate functions. First, air is passed through an electrode chamber, the cathode, where oxygen from the air is charged with electrons to form oxygen ions. Next, the charged oxygen flows to the other electrode, the anode, where it reacts with a fuel gas, for instance as here with hydrogen. But it could also be natural gas or biogas. The transport occurs through the electrolyte. The electrolyte works as a one-way ticket. The charged oxygen can travel in one direction, but the opposite direction is closed. The electrolyte is very thin, only about 1/100th of a millimeter. The charged oxygen can therefore easily travel across to the hydrogen fuel gas, where the atoms react to water, H2O. Left over will be the excess electrons from the charged oxygen. They will try to return to their origin, the cathode. But since the electrolyte blocks the way, they will have to travel in a wire, and electrons traveling in a wire, that is current.
Seminato, did you guys hear the
Yes.
video? Any questions? Questions about the video?
Yes, I didn't understand why they said it reduces the losses of the distribution energy when using these cells in residences.
Yeah, so what he means is because in Europe, for example, in Norway, they have a lot of district heating systems, and when you have centralized heating system, district heating systems, something like 20-30% of the heat that you distribute is lost to with the pipelines, tanks, with the whole system. If you're generating heat inside the house, so the boiler, the appliance that is generating electricity inside your house, if it escapes to the environment, it's gonna heat up the house. So you lose less heat by providing the heat right up where it's needed. So that's why he says that it's better to burn the methane in your house than burning in a district heating system and having to transport the heat to your house.
Okay, it makes sense. Yeah, thank you.
So what did you guys think? Do you like this type of it's just to kind of better comprehend what I tried to explain last lecture. I just think that is a better way to solidify what I said. So I was actually interested to show you 2 more videos. If you guys think that this works, up to you guys. What do you think?
I agree.
I like
Okay,
it. Yeah, I learn a lot.
Okay, awesome. So there are 2 more videos which I really think that's interesting for you to watch. So this one wasn't extremely relevant for Brazil because Brazil is a very hot country, right? So maybe for the south of Brazil, like Rio Grande do Sul, but here, but not really. But this one definitely is more applicable to Brazil. So I'm gonna start the video. Do you guys want to start also?
Nissan's goal is to realize a zero-emission and zero-fatality society. Nissan Intelligent Mobility is a strong drive to achieve these goals. This is a vision to make our cars more exciting by redefining how they are driven, powered, and integrated into society. Now, we are about to pursue the next step and apply our EV technology here in Brazil, using an alternative fuel source.
This prototype runs on a solid oxide fuel cell SOFC powered system, what we call e-biofuel cell technology. Unlike conventional systems, it uses bioethanol fuel to generate electricity through the SOFC. This increases the driving range of our electric cars while reducing battery charge time.
We think this is a natural next step for our intelligent power vision.
The use of electrical vehicles can be amplified and be more efficient while utilizing existing infrastructure. And that is where bioethanol fuel comes into play.
With SOFC, the electric vehicles will have a cruising range of more than 600 kilometers, while retaining the distinct advantages of electric mobility: its range startup, its silence, and brisk acceleration.
Commonly produced from sugarcane, corn, or soy, this form of fuel is widely available in North and South America.
Hydrogen is produced through reformation of ethanol in the SOFC system. Then the system uses this hydrogen to generate electricity.
A small amount of CO2 is produced when ethanol is reformed into hydrogen. But these CO2 emissions are neutralized with a process of growing these plants, allowing for a carbon neutral cycle.
Nissan will continue to promote a future with intelligent vehicles and electrification. We expect our e-biofuel cell technology to be ready as early as 2020. Our EVs combined with alternative sources of energy will be clean, efficient, and fun to drive. We want to provide value to our customers by bringing exciting new ideas to our EV family.
Right, so this was the other video. Before you guys have any questions, let's just hear the next one, which gives more details into how the system works. This was just to give an idea, more overall idea of the benefits. Of course, ethanol is more competitive than hydrogen. I mean, ethanol is competitive with gasoline today. Hydrogen is
we're
10
seeing
times
more
more
automakers
expensive than gasoline. So it's a solution in order to improve ethanol, because you have higher efficiencies. Ethanol engines have 25% efficiencies. These have 50% efficiencies. So with the same tank of ethanol, you can go around twice as far. And also you have batteries inside. So when you break the car, you recharge the battery because it's a hybrid system. So it has several advantages. And yeah, well, it's a great solution for the Brazilian electricity sector, particularly because as I told you, as I mentioned before, there will be no ICE engines in the future, because no one probably, I mean, I'm not 100% sure about this, but definitely the number of automakers that will produce ICE engines will stop. So the supply of ICE engines will reduce. So you'll have to find other solutions, and fuel cells will be plenty in the market. They'll be available. They'll be much cheaper than today. So it's good to start thinking of how Brazil should supply the demand for transport, for example. So let's listen to the second video.
Test out fuel cells, but there's still an issue with fueling infrastructure. Now Nissan may have come up with a solution. It's developing a fuel cell that can run on multiple fuels, mainly ethanol and natural gas. The system generates electricity through its solid oxide fuel cell using stored bioethanol. Solid oxide refers to the cell's electrolyte material. One of the biggest advantages is that, unlike other systems, no additional CO2 is emitted when power is being generated. It also offers better long-term stability and lower overall cost.
I guess just the first part was the important one. Talked about the it shows. Let's go back. So this is the representation. Basically, you have the tank with ethanol or methane, as you said, and you have a reformer which turns the methane or methanol into hydrogen and CO2. So you have hydrogen and water. You have a steam reform system, and then this hydrogen with water goes through the tank. Through the solid oxide fuel cell, produces electricity and water also. Then this water is recycled in order to provide more water for the steam reforming cycle in here. So you have air which passes through the oxygen, that passes through the oxide fuel cell, produces more water, which is recycled in order to provide more water for the steam reforming cycle. So it's a very clever system that recycles the water for the steam reforming, to reform steam, to transform ethanol into hydrogen. You need steam, which is also a byproduct of this solid oxide fuel cell, and then you produce electricity. You can either store the electricity in the battery or use electricity for acceleration. Also, it's always good to have a stored battery, because a fully charged battery with this system, because solid oxide fuel cells take a minute or two in order to provide full potential, full power, because they have to heat up to 700 degrees, as I mentioned to you in the last lecture. Any questions? Okay, so let's start the lecture on batteries. So this was just
sorry, I was
yeah.
unmuting myself. How about the costs?
Natalia, do you have a question?
Sorry, my microphone wasn't working. Okay, I have just a question about the costs. It's like,
they didn't release the costs. I couldn't find it. I looked for the costs of the system. I couldn't really find any information on the cost, particularly for this type of car.
okay.
But comparing here, we have in this table a general cost. So for fuel cells, the cost is for solid oxide fuel cells, the cost is around 10 times higher than proton exchange membrane. So the cost is essentially higher, mainly because you don't have so many systems being built today with this technology. Most of the investment is money is going for this proton exchange membrane. It takes over most of the market. But of course, this cost can be significantly reduced if a lot of people invest and start using this type of technology.
Professor?
Yeah.
Do you know how the efficiency of 1 liter of ethanol to produce power to the electricity farm? Because I want to know about the needs to crop and to plant more crops of sugar cane.
That's a great question. Let's have a look. I have the diagram that shows. I can't find it. Where is it? Maybe here. Yeah. Ethanol, with one liter of ethanol, you produce it's something like 70% of gasoline, of the amount of heat that you carry by weight. So with 1 kilogram of ethanol, you have something like 30 megajoules of energy. But the interesting thing of this system, instead of using an internal combustion engine, is the efficiency. Because going back to this table here, you have the efficiency 50% of the system. It could reach up to 60%. Ethanol internal combustion engines are usually 25% efficient. So you would need to produce in Brazil half the amount of ethanol if you're using this type of engine, just because it's twice more efficient. So instead of, for example, if you drive to work and you have a car and you spend a month 500 reals, if you buy another car with this solid oxide fuel cell engine, you spend 250 because you consume half the amount of fuel. So that's why they are so worried. That's why they're developing this. If not, you might as well just use a internal combustion engine. But I also mentioned to you that in 20, 30 years time, we won't have internal combustion engines because Volkswagen are not going to sell us internal combustion engines. So if you're thinking of investing in a project, developing a project now, this is an interesting project for Brazil because Brazil has a lot of ethanol, which is a cheap, sustainable energy solution for transport sector. Did I answer your question?
No, yes, it was pretty great. The efficiency I was not aware about. My only concern is about the deforestation to plant new crops. But with this rate, it's pretty good. It's better than change for 100% internal combustion utilizing ethanol.
Okay, thanks for worrying about the environment, Renan. But the thing is that we have a lot of land in Brazil. We only use something like 10% of the available land for agriculture in Brazil. So we have 90% of agricultural land that we could use. And yeah, of course, we would want to deforest more of the woods. Of course, we would try to reduce as much as we can. But with the land that we have now, if we completely stop deforestation, we still have enough land to supply Brazil and probably even Europe's demand for fuel. So there is a lot of land. And sugarcane is not the main.
In that scenario, we have to change the crops. Stop using, I don't know, rice to grow sugarcane.
Yeah, so this was a huge concern, for example, that stopped Europe investing in biofuel. But the thing is that Europe has very shortage amount of water. Brazil is the country with the most water in the world. We have more water than Russia. Russia is about 5 times the size of Brazil. We have a lot of land, so land is plentiful. Of course, we wouldn't need to deforest more. So the choice is that either we plant or we don't. So it's not like we have to choose between rice or sugarcane.
We always can start grow tobacco and put some sugarcane.
Yeah, we can stop growing tobacco. We can stop growing, for example, soybeans, because soybeans takes over most of the arable land in Brazil, and the soybeans that we produce, we sell to China, so that China can feed the swine. So pigs.
Yes, we have.
In order for eating, China eating pigs. They don't even eat the soybeans that we produce. It's the pigs in China that eats the soybeans. So maybe we can start developing technology. Maybe we can start creating a country from the ground with our own expertise and stop selling soybeans for Chinese pigs. So there's a lot of possibilities in the future. So
we just can't stop to grow coffee. Coffee must remain, and the rest.
Coffee must remain, definitely. Yeah. Without coffee, there is nothing we can do anything. Any more questions about last week's review? Action review?
Yes. What's the expected lifetime for a combustion cell?
For an internal combustion engine, probably it depends on the engine that you buy. If you buy a Honda Fit, for example, it can take something like 20,000 kilometers, 200,000 kilometers, which is a lot. If you buy, for example, a Fiat, then probably 100,000 kilometers. You will have to go through a lot of maintenance, which will increase the cost of the engine. And then maintenance costs are high, which will probably cost the price of a motor in order to continue using it. Was that, did I answer your question?
Yes.
So I'm gonna leave you guys with this video here. It's about proton exchange membrane. I'm not gonna go through it now, but it is interesting. It's alternative. So this is the mainstream fuel cells that are used for transportation around the world. It's not what I suggest for Brazil, but it's an interesting alternative. So the reason, yeah.
Oh, sorry, I thought you finished. Okay. No, I was gonna say that when I was in my graduation program, I did a work about fuel cells in data centers to generate energy from the heat that come from the refrigeration of data centers. That was a really big issue, energy for data centers that can be addressed too.
So you wanted to generate electricity with the heat from that data centers with fuel cells?
Yes.
How did it work?
I didn't. I just had like the, how can I say, a literature review about it, that it's possible, but I didn't actually did the work, but I read about.
Yeah, I think, you know, I think you don't mean fuel cells. You mean the term, I forgot the technical name. There is a technology which uses temperature differences in order to generate electricity.
Oh yeah, probably. Yeah, you're right.
The thermodion. It's not energy storage, so I don't think we should address this in this lecture, but it's an interesting aspect, which, yeah, exactly, as you mentioned, you don't need to burn a fuel, you don't need to evaporate steam to generate electricity, thermal electricity. You just use
the difference.
The panel.
The difference of temperature. Yeah, you're right.
Within the panel, the difference in temperature produces electricity. That's not a fuel cell.
No, yeah, you're right. I'm making confusion. Yeah.
You have to pass the ions through the electrolyzer. Okay. Thanks. Any other suggestions, questions?
Julian, just a quick question regarding application in cars. How is the weight of these fuel cells compared to batteries, traditional batteries?
It's a good question. So, of course, batteries are very heavy. If you have a lot of, if you want to go very far, of course, the batteries are heavy. But also, these systems, these fuel cell stacks, they also have substantial weight, which adds to which makes the system heavy. Also for hydrogen, you have to carry the hydrogen. The hydrogen is very light, but the tanks, if you want a pressurized tank that can sustain 700 bars of hydrogen inside, the tank itself is 100 times more heavy than the hydrogen. The hydrogen is too light, but the tanks to sustain that pressure is very heavy. I haven't really looked into this. I didn't think about it. It's a very, very good question. So I'm going to take a note and I'm going to answer you the next lecture. Is that okay?
Okay, thanks.
Thank you. Very good question. Yeah, so the reason why I insist in this solid oxide fuel cells in Brazil is that you can use methanol. For example, when you have an energy crisis and you need electricity in your grid, and you have like, ooh, we have a drought, we are suffering, we don't have electricity to generate hydrogen to run these fuel cells. Okay, we have a lot of ethanol which we can store in storage tanks, and we can increase production next year and then supply the demand for ethanol. But if you have a lot of electricity, for example, it rains a lot, and then you have a lot of hydropower, and then you don't have what to do with this electricity. So you produce cheap hydrogen, and then you supply these cars with hydrogen, because they're very flexible. You can use hydrogen, you can use ethanol, you can use both in the same fuel cell. They're very flexible. So this flexibility will increase the energy security of the country, because you can play with these reservoirs. Hydropower reservoirs are low. Okay, let's start using ethanol. So next year we start producing more ethanol in order to reduce consumption of electricity for production of hydrogen. So this aspect, by the way, I just thought about it now. It's a very good paper. Somebody, if you want to write a paper, good paper about this and write and then get a lot of citations, feel free to use it to write a paper. So that's one aspect for Brazil, why these solid oxide fuel cells are very interesting. Any other questions? Okay. So let's start the lecture. Lecture 6, batteries. So batteries are within comparing the need for energy storage and power storage. They're in between the middle. They supply a lot of power to a grid, to whichever need for power you need, you can supply power, but also they store energy. They are not as good for energy storage compared to pump storage or hydrogen, because you need a lot of batteries in order to store a substantial amount of energy. For example, having batteries for supplying grid demands, so storing electricity in the grid, for example, for transmission lines, 100 megawatts batteries, they exist nowadays. They are not competitive with for example, pump storage. The prices are coming down. But, so you need a lot of batteries, right? Which it's, you need a lot of components, you need a lot of materials, and these systems are modular, so you can do, but it's not, they weren't really designed for supplying grid storage. It probably will be used for grid storage in the future. But for example, if you're driving a car, so the car is sitting there and the batteries are sitting there, and you want to step in the pedal and then rise the temperature really quickly. So you need very small amounts of time that you need quick power. So that's a good thing. That's what batteries are designed for. And then they sit there for the rest of the day, and then you need to drive your car really quickly, go to, I don't know, go to work, and then you use the car. So their usability is only 5% capacity. So they are just used for certain times to provide large amount of power for short amount of time. So they're very interesting for power delivery. Not so much for energy, but given that the costs are reducing, we will see batteries for energy uses more frequently in the future. So about the theory, so the theory of a battery, what's the theory behind a battery? You have a cathode. I don't think the cathode is written on the sorry.
Tudo bem,
No.
graças a Deus.
Cathode.
E contigo também, que vocês também.
I wrote this. So,
Ai, que bom.
I'm sorry. Cathode, electrode, and anode. So the cathode is usually a metal that you use. It's not always a metal. It could be a gas, it could be a liquid. which is positive charge. So it wants to oxide. It wants to gain electrons. It has a positive charge. It has a lack of electrons. So electrons wants to go to them. And then you have an anode, which could be a metal, could be a liquid, could be a gas. And they are negatively charged. So they want, so this type of metals, they want to release electrons. So they, for example, they don't want to be in oxidation levels. They want to, for example, in nature, if you have them in nature, they wouldn't be an oxide, for example, because it's not their natural state. For example, gold could be a good anode, for example. And so what happens is this desire of not having electrons or having electrons provides a difference in voltage between them if you connect these two cells with an electrode. So in this Daniell cell, which is the most basic cell, what happens is that if you create this bridge, which is literally it can be a towel with a a towel diluted in salt water. The ions, for example, copper ions, which are dissolved in this aqueous solution, it will travel from one side to the other. And the positive ions, so when the ions come from this side to this one side, electrons will flow from the anode to the cathode. And what happened is that the zinc, given that the balance of ions here will become positively charged because of the copper travels to the side, one zinc will lose zinc will lose electrons, and then it will deposit zinc into the anode, so the anode size will increase, will become solid zinc, and the electron produced from this will flow on the other direction. And then the opposite side, if you want to, so this is the natural flow, negative to positive, and then you generate electricity. If you want to store electricity, you have to put a voltage in the system. So you put energy, you want to charge this battery, you produce voltage, which is man-made voltage. So we're putting voltage in the system, so the opposite thing happens. The copper flows back to the sides, zinc dissolves, but in order for zinc to dissolve, it needs 2 electrons, and then the electron will flow from copper to zinc. What happens is that the copper, which is in the aqueous solution, will build up in the cathode. So the copper on the aqueous solution will react with 1 electron, which is coming from the zinc side, the zinc cell, and then it will build up copper in this side. And this is a reversible cell. So this is a cell which you can recharge as many times as you want it until the system starts, the voltage starts to reduce. So you use, the voltage of the system will reduce because you have a lot of copper ions here, you have a lot of zinc ions here, they're gonna be floating everywhere. So they're gonna reach an equilibrium that you have too many zinc ions here, you have too many copper ions here, which will affect the amount of zinc that you have to solidify again. You have less copper to solidify or dilute in the system, and then the voltage starts reducing. And then you need to buy a new battery or somehow recycle this, separates the copper ions with the zinc ions, which is complicated and costly. So generally you just throw away the battery build a new one, buy a new one. So this is a table which shows the reduction half reaction is the state of oxidation. There are, for example, gold. Where's gold? There's no gold here. So, for example, iron. Iron is a metal that there is a lot of iron in the crust. Iron wants to oxide, so it's positively charged. So if it's in the environment, it's out there, it's going to become positively charged. So the stronger the oxidation agent is, so these are the stronger oxidation. This wants to be oxidated, become to react with oxygen, and these ones they don't want to react with oxygen. And the difference between these potential creates a voltage difference. But each of these cells, the limits, the theoretical limits, can only produce 1.1 volts. In order to increase the amount of voltage that you have in your system, you can either have this small voltage with a high current go through a substation. So have a bar of metal, and then roll it around, and then connect with another one which you roll more times, and then increase the voltage like this. You have one battery, increase the voltage artificially with a substation. Or what you can do, you can add more of these batteries on series. If you add batteries on series, you add the voltage. So if you have two of these systems in series, you have 2.2 volts, 3.3 volts, 4.5 volts, 5.5 volts, and so on. But one system, if the ion goes from one side to the other, this is the limit, voltage limit that you have. This is the theoretical part of battery. And the funny thing is that if you see fuel cells versus batteries, what's the difference between fuel cells versus batteries? Actually, a fuel cell is a battery. No, sorry. A fuel cell is not a battery, but a fuel cell works similarly to a battery. In the way that you have hydrogen, which has a zero, I forgot particularly what's the name of this E, sorry, but it has a zero potential for oxidation. And however, hydrogen combines with I forgot the name of this. It's
hidróxil.
Does anyone?
Acho que é.
Hidróxil.
Hidróxil.
Eu acho que é.
Eu acho que é também hidroxil.
So hydroxyl. So hydrogen combined with hydroxyl produce water and electricity. And then that voltage is 0.83. So this is a theoretical voltage of a fuel cell. This is a theoretical voltage of a fuel cell that you have. Of course, assuming some parameters, which is in order to calculate, which is something like around, if you have a current of 400 mini amperes going through at a certain temperature. So assuming that the temperature increases a certain amount with this process, this is the voltage that you have with the fuel cell. Looking at the system, of course, the cell of each fuel cell between one fuel cell will vary. not only the fuel cell, but batteries also. But fuel cells, they have particularly higher voltage reductions compared to batteries because the size of the hydrogen that has to go through this electrolyte is very tiny. So it's very difficult to create a cell which only allows protons to pass because it's a very small membrane. And then you lose voltage in order, so this voltage you lose passing the ions through the electrode in order for the cathode to absorb the oxygen in the cathode, in order for the oxygen to split into ions and go through, because this is a proton exchange membrane. So the hydrogen passes through the electrolyte, which is even tinier than oxygen. So there are, in some cases, oxygen passes through hydroxide, the oxygen, hydrogen minus ions. So it takes voltage in order to split the hydrogen cell in the anode. Then for the ions, hydrogen ions, to pass through the electrode, also you lose some voltage. You lose voltage for the oxygen to combine with the hydrogen protons that go through the electrode, and you also lose voltage in the electric system. For example, if you want to turn the electricity from DC to AC, you lose voltage in the cell because the cell will have less, will have a resistance here in order to allow the system to work. So all these affect the fuel cell voltage. So going back to talking about fuel cells and batteries, this is an interesting aspect. I kind of had this in mind, that the fuel cells work similar to batteries, but reading like through the literature and stuff is very interesting to see that batteries and fuel cells, they are very similar concepts. So for example, fuel cells, there are a lot of batteries that use fuel cells, for example. We're going to talk about the redox flow batteries, as one of you guys asked me to look through, and they use fuel cells within the batteries. So the main distinction between batteries and fuel cells is that batteries are used to store energy. So batteries is a system used to store energy. So you put electricity, and then you take electricity out. And then in the system, maybe you have a fuel cell there, but a battery is something that you charge and then you discharge. Fuel cells, they can be used in batteries, but the main, instead of saying batteries, you say a fuel cell. When you put fuel in the system, for example, hydrogen, you put ethanol, and then you come out with electricity. You don't recharge a fuel cell. Fuel cell is just used for producing electricity. And then within batteries, you have two main types of batteries. So these are the type of batteries. These are fuel cells. So you have primary battery, which is a battery which you generate electricity with the battery, but you don't discharge. So it's a, for example, a battery that you use in kids' toys. Nowadays, no one buys those AA batteries, AAA batteries, A batteries. Those ones that you buy in the shop, the supermarkets. Every counter you'll find these small batteries that are not rechargeable. They are battery because you will have this packet you put there. You can't call it a fuel. Maybe you can call a fuel, but they're called battery. And then you put them and you use the electricity that they produce, the charge, the power, and then you can recharge it, throw them away. And then you have the second type of batteries, which are the ones that are becoming more and more relevant in our lives, which are secondary batteries, which are the batteries that you recharge. For example, in your cell phone, you have your laptop, and these are the secondary batteries. And then you have fuel cells, which I already explained the difference between batteries and fuel cells. Any questions about the difference of batteries and fuel cells? Okay, so let's continue. So there are several battery types. For example, lead acid is a battery that we use in cars just to give the power in order to turn the ignition of the motor to start running. Maybe if you turn off the car, you want to listen to some music, you want to turn on the lights to have a look. So it doesn't really store much energy, but it gives a good amount of power to start your car. The energy density is around 30 to 50 watts per kilogram. For example, compared to lithium ion batteries, they go up to 200, 130, 120. So you have different types of lithium ion batteries. Of course, the cobalt one is getting most attention because it has a higher specific energy density. And we're going to talk about cobalt a bit more, I think, in the next lecture, because we won't have time in this lecture, but there's a lot of challenge on mining cobalt. So it turns out that cobalt becomes more expensive than actually lithium. So it's difficult to mine cobalt. It's very environmental. It has a lot of impacts to the environment, and there's less cobalt than lithium. And lithium-ion batteries require a lot of cobalt in order to reach this very high energy density. Life cycle of lead batteries, small. For example, every 2-3 years you have to change the battery for 4 years, 5 years, depending on the quality of battery they get. We have the motor, for example, of the Brazilian lead acid battery. It charges, takes a significant amount of time to charge. Several different characteristics, which I don't need to go very much in detail. I'll leave the slide here for you guys to see. It's a nickel cadmium battery. It's also a different type of battery, which are also used for cars, but not in Brazil, different countries. Nickel, I'm not sure what this MH means. I didn't really look through. But yeah, there are several different batteries. They have different characteristics, and whichever service you need or to be supplied, you will find an ideal battery. I think this slide should have been before that one. So an example of primary battery, which is the one that you charge, for example, empty those Discmans in the past that we used to listen to music when we didn't have iPhone or mobile. They are zinc manganese. So the zinc is actually the metal that the battery is made of. So it's made of zinc. So the actual pack that you have, the battery is consumed. So the zinc provides the structure of the battery, so it makes the battery hard and stiff, and also provides the ions in order to produce the electricity in the batteries. You have the cathode, which is carbon, the electrolyte, I'm not sure what it's made of, and the cathode. The cathode is usually this manganese, the zinc manganese, and it's cheap. Zinc and manganese is cheap, so that's why it's make it easy just to build some and throw away. So it's not like so it's viable. It's a viable alternative. It's still viable today. People are still selling this type of batteries. Oh, the electrolyte is potassium hydroxide. So that's why they're called alkaline batteries, because potassium hydroxide, it's an alkaline, which allows the zinc to flow through the electrode and then reach the cathode, generating voltage and electricity. And the secondary cell, I already talked about it in the first slide. So I don't want to talk about it again. So battery energy densities is one of the main issues, the main concerns of batteries. So what you need really with batteries is something that provides you electricity, provides you energy, provides you power, whichever needs you want. And of course, you want it to be as light as possible. If you're using for transportation, if you're using for gadgets, if you're using for grid control and it's sitting there all day, it doesn't need to have very high energy densities. It needs to be cheap. It needs to provide the service reliably. It needs to have long life cycles so you can reuse every time again. But energy density is very important if you're using batteries for transportation. So as I show you, lead acid batteries, low energy density, nickel cadmium, low, nickel metal hydride increases a little bit. Lithium ion batteries, much higher, reaches up to 300. I think the theoretical, I'll show you some slides, the theoretical limit. Have lithium phosphate, lithium polymer, different types of batteries, and then going through even further with batteries which are not yet commercial, which are still in developmental stage. For example, we have lithium oxygen, which is also called lithium air. I'm going to go through in the end of the lecture. It has a very high energy density, close to even gasoline. So it's as if you have a battery which has a similar energy density to batteries. But it could reach the point. It could reach the point that it's so expensive to have this lithium oxygen battery that you might as well put hydrogen inside your car. So these batteries are not only competing with themselves, they're also competing with hydrogen. You could even have a hydrogen battery, which makes no sense, but at least the hydrogen battery, what will happen is that in the end so you have a hydrogen car, which instead of filling up with hydrogen, you have to charge with electricity. But of course, the weight will increase because you have to carry the oxygen. While you run your car, you're producing water, and then as much water that you produce, the heavier the car gets, and then the heavier the energy density of using the solution. So the lithium oxygen has this issue. So you use the lithium oxygen when you start to drive, so you fill up you charge your battery. When you start to drive, the battery starts to become heavier and heavier because it takes oxygen from the air, and then the battery becomes heavier as it goes along. So there is a redox flow lithium battery. There is the batteries. I'm going to talk about the vanadium flow battery, which is for grid energy storage, and several other ones, which I'm not going to go into details. So this is another study. It's a paper showing that lithium air can have a gravimetric energy density similar to gasoline. As I mentioned, this is when you start to drive, this gravimetric energy density reduces because you add oxygen to the system. So lithium ion battery, this is 160, is very low. Today we already have 250 lithium ion battery densities. So of course, with technology development, this value is increased. So comparing different lithium ion batteries, we have the cobalt one that exists today, can reach up to 500. These are the theoretical values. So 500 is a lithium cobalt ion battery. You have lithium manganese oxide, lithium don't know what this metal is. Lithium oxide, lithium, in short, how do you say it? Sulfur, lithium sulfur. Sulfur has a very similar characteristics to oxygen, for example. There's even animals that breathe sulfur on the deep ocean, so they usually have similar characteristics. Why oxygen? Because oxygen has a very high oxidation capacity, right? You even say oxidation because of oxygen, so that's why oxygen is the highest. Lithium wants to be always not oxide, not an oxide. You have sodium. Compared to sodium, sodium is much heavier, so it has a lower energy density. Manganese can reach very high with oxygen also. Aluminium can reach very high energy densities with oxygen also. Zinc, not so high energy densities. Comparing only lithium batteries, you have even the fluor is higher. So fluor is higher than oxygen. You have oxygen, fluor is higher. Cobalt, the ones that we're using today, very small. So there's a lot of room for improving lithium-ion batteries. It might not reach the point that we will use all of them because it could be too expensive to develop, and then in the future hydrogen will become cheaper. So we go for hydrogen, which is so I showed you in a lecture. Hydrogen is 40. So instead of 7 here, you have 40. So it's 6 times better than the lithium alternative. 66, around 6 times better than the lithium alternative. Very high energy density for hydrogen. They show you here hydrogen, you're here, you have lithium. So this is lithium oxygen battery. Is literally, if you have a lithium as a metal and you burn it, it's going to explode. It's going to have a huge explosion because it contains a lot of heat in the metal. But of course, if you put it in a battery, you don't burn it. You transport ions from the cathode to the anode in order to be able to recharge afterwards. Aluminium is substantially better for volume. So if you want to use a battery with very small volume, aluminium is the solution. You wouldn't want hydrogen, for example. I don't know exactly which type of applications you would want a battery to have a very small volume. Maybe if you're putting something on your heart, which has to be very small, and you need a battery there, and yeah, you use aluminum air battery because it's going to be very small. It's not going to be on the way. Maybe for medical applications. Zinc also has a very large volume, and storage is a little bit smaller. Is a bit higher. Weight also, which is convenient also. Other ones, sodium. I showed you sodium before. Zinc air, so zinc air battery. So all these metals, they are batteries. Magnesium battery, lithium bromide, iron, zinc. Right, so now talking about particularly how a lithium-ion battery works. The lithium-ion battery has an anode, which is usually structured with graphene structure. Nowadays, graphene is already deep enough, so they already exist, and they stack the lithium. So they organize lithium in order to flow to the anode. And the reason why lithium would want to flow to the anode is because this MO2, which is a metal, I don't know what M stands for, but this cathode, it's very has a very high oxidation capacity, so it creates a voltage difference. So if you connect this, this electricity connection, what happens that electrons will flow through, will generate electricity, and then the lithium ions will flow through the electrolyte. If you stop the current, it stops the flow. Of course, the electrons cannot flow through the electrolyte because it's doesn't allow current to go through, so the current has to go through this system. The anode here is copper and the cathode is aluminum. So this is one lithium ion battery. There are 1,000 different lithium ion batteries with different anodes, different cathodes, different structures, different electrolytes, and each one has different costs, different capabilities, different complexities for construction. So here we can compare lithium cobalt to lithium manganese, lithium nitrogen. This M, I don't know what this M stands for. If somebody could have a look and tell me, that would be great. Carbon, phosphate, nitrogen, carbon, A. I don't know also what A stands for. So some of them have low costs. So this one has a low cost, but of course it has different characteristics, which is not appropriate for some application, but it's great for other applications. So the thing is that you can always find the best lithium-ion battery for the applications that you want. In this analysis, you have costs, specific energy, which is how much, what's the weight in order to provide energy storage, and this is the weight to provide power. So then what's the weight and the size of the electrodes, which has an impact on this. Maybe the electrolyte, right? The electrolyte has to be very big, and then you lose power. If the components are lighter, which stores the energy, then you have higher specific energy. Safety is a very big concern because lithium-ion batteries, for example, if you have shortcuts, if you have problems that they discharge the energy that store really quickly, they can explode, they can produce heat and can damage, kill people. You know, for example, in a plane, if you get in a plane in Europe, I'm not sure in Brazil, they always ask you to turn off the phones because the chances of phones exploding increases if they're turned on. And exploding phone, what happens is that it has a potential for killing people. It will throw gases to the plane, which will be toxic gases and could even result in the plane having an accident and killing everyone. So very important issue. Everyone has a phone nowadays. You don't want to hear in the news that every 2 months that somebody died using their phone. Performance, the power capacity that you have is the amount of current. So if you lower the if you lower the charge, usually these lithium-ion batteries, you cannot lower the charge so much. For example, lower than 10%. If you lower than 10%, then you lose the capacity of the battery, and then you lose performance. So this is one particular issue. Lifespan, how many cycles you can store. If you store energy, how many days can you keep the battery charged before using again. So different characteristics which require different battery solutions. The lithium-ion battery, for example, this lithium-ion battery, you have the cell voltage will reduce the amount of lifetime that you have according with this line. So you have a battery that lasts for 1.5 hours, but the voltage of the battery will be reducing. So if the voltage of the battery reduces, what happens then it has to increase the flow, so the current, in order to provide the same power. And of course, if this line can be as flat as possible, is also a benefit for the battery. when it's very charged, when it's fully charged, you need less currents, so you save your charges, your ions. Not so many ions need to cross the electrolyte. So, for example, if you're using your battery in this state, you have less ions going through the electrolyte. If you're in this stage, you have more ions going through the electrolyte to supply the same power. I didn't put the equation here, which tells how the power works. I don't know from the top of my head, I'm sorry, but it's I'll show you in the next lecture. Constant current charging. So when you want to charge on the other side, on the other hand, so the battery is discharged, what happens is that you cannot take a very high voltage in the beginning. It has to go slowly increasing the voltage. And the voltage has to be small, not to shorten the lifetime of the battery. Starts slow and slowly increases the voltage. Then when it's fully charged, then the voltage is at maximum. So you need a very high voltage in order to make sure that you charge it fully. And the charge and the voltage has to be smaller in the beginning when it's empty in order to charge it. Usually batteries has this Coulomb counting region where it's the voltage which the battery operates. When the battery reaches this point, it stops operating. Maybe for safety reasons, they will even lower more in order to increase the lifetime of the battery and things like this. And then after this point, the battery stops because you have a very large drop of power supply in here, and it wouldn't really make sense to make use of this low voltage section, because then the amount of energy that you store here is very low. You need too many lithium ions to go through, and it's just not optimal, so you don't use it. Interesting aspect also is that lithium-ion battery should always have the same charge, both in using the batteries, both in when you use the battery or when you charge the battery, because the voltage, for example, this battery here has a voltage which is smaller, and then what happens that the voltage that would dictate the system would be this. So all the other batteries will have to discharge more ions. So the efficiency of the system will reduce. So you need, so your battery lifetime will be very small. For example, if you have a TV control and you have two batteries, they are dead, and you're not sure if both they are dead, it's not a suggestion to change only one. It's always good to change both. If you change both, you optimize the use of the cell of the battery because of this voltage and current issue. But charging is the same issue. If you apply a larger voltage for a battery that is uncharged, what happens is that you just lower the lifetime of the battery. Nowadays, we don't have these rechargeable batteries. In the past, we had rechargeable batteries that you put on a wall and then you charge them. And then if you have one that's fully charged and two that are not fully charged, what happens is that the one that's fully charged, I think the one that have low charge, they will receive a higher charge, and then they will damage the cell quicker. So the lifetime of the cell will reduce. To talk about lithium-ion cell batteries, I only have half an hour. So the design of a lithium-ion battery is that you have these insulator, lithium foil anodes, polymer, electrodes, cathodes, and currents collector. So what happens that each of these lines provides one battery cycle. So for a lithium-ion battery, I think the voltage for a lithium-ion battery is 3. Let's see the voltage, 3.6, 3.8, 3.3. So each of these cell voltage has, each of these lithium-ion battery has different voltages. So for example, nickel cadmium has only 1.2, nickel MH 1.2, lead acid 2 volts. This is important, but this is very high lead acid volts. Why? Because they need the power. So the higher the voltage for each cell, the higher the power, and the power is very important for turning on the engine of a car. That's why the voltage is high. Lithium-ion battery has very high voltage also, and they are designed specifically to have high voltage because you want as higher the voltage as possible in order to use the least amount of ions, the least current, in order to have the same amount of power. This is why they have very high voltage. And the other things that they do that they roll this. So each of these rolling sums the battery. So you have, for example, 3 volts here, 3 volts here, 3, 3, 3, 3, 3, 3, 3. Let's say you have 100 times that you go around, you have 300 volts. 300 volts is equivalent to the amount of energy that you get from your 220 volts from your house. It's huge amount of voltage. So it's like if you stack these. So for the solid oxide fuel cell, they stack them because they are rectangles. And in order to optimize the volume, Tesla batteries, for example, they have this design where they roll these sections, which is the insulator, the anode, cathode, electrolyzer, and current collector. And the voltage increases. The higher the voltage, the less battery you need. So that's why it's very important. So designing a battery is something extremely interesting, complex, and that's why there are so many car companies competing, and the best one, the most clever automaker will find a great solution, the great balance, the great design that will power the future of humanity, right? Because we're going to be driving this battery car. This is a Tesla battery. Tesla battery, they have 700 individual cells. So they have these cells, which are similar to these ones, and they're stacked. They're not so small. The new version, they're not so big, they're quite small. The new versions, they are becoming more thicker. The thicker it is, the higher the voltage, because they have more rolling around. The longer they are, the more energy they store. So Elon Musk likes to make them very thick, to get a lot of power, voltage, in order to require less current. So they stack this battery on the bottom of the car in order to make it more stable. Because the lower the weight, the more stability the car gets. What else? The entire battery pack weighs 1,200 pounds, which is times 3, 4,000 tons, 4,000 kilograms, or 4 tons. The car probably weighs 6 to 8 tons, and the batteries weight 4 tons. Very heavy. Just comparing a battery with a Tesla battery, it's a little bit bigger. Right. So the battery has the positive side, the negative side is similar to this batteries that we buy in the shop. The design, of course, but of course inside is very different. You have these components that I showed you before: cathode, anode, separated, the connector, and they have 1 gram of lithium each. Very, very small amount of lithium. So the cathode has 2% of aluminum, 73% of nickel, 14% of cobalt, 11% of lithium. I guess this is weight related, so it's the percent of the weight. So of course lithium is only 11% of weight, but lithium is very light. So it might take something like 30 to 40% of the volume inside the battery. The cathode is carbon. It's probably this one, graphene. What happens is you have a lot of lithium in here, which is ready to be discharged and go to the cathode. So the cathode pulls the lithium, which is stacked in this carbon-based structure that is kind of a shell, which you store the lithium ions there. I don't know if I'm explaining this properly, but this is kind of the way that I understand the system. I'm not sure if it's being clear to you. If you guys have a question, please let me know. Batteries sound very complicated. Oh my God, this is like crazy stuff. No, it's not so crazy stuff. It's just it takes a lot of money, efforts, and having to invest. And it's very intensive work for optimization. So it's for people that lab rats, but like they really like to go in the lab and to test new alternatives, test new things, and really like details. To look at details instead of thinking broader terms, what should we do today, blah, blah, blah. No, planning stuff, no. So this is lab rats, people that really like to go into very details on the other stuff. So looking more into the market for EV, we have that today, not today, but 2017, the annual global vehicle sales will hit 25 million in 2030. So this is the projections. We are here today and it's going to increase substantially. These are the projections from Bloomberg. Bloomberg is a very good, reliable source for projections. Yeah, so it's gonna happen, guys. For example, Norway, Netherlands, Germany, India, France, UK had laws passed that they'll stop producing ICE vehicle designs. As I said in the last lecture, UK decided to lower this to 2030 also. So they'll stop using internal combustion engines. They're going to use battery instead. China's planning, people don't know about China. Then the automotive cars, they have also given indications that they will increase EV. So Volvo will stop. Okay, Volvo stopped. Oh, Volvo doesn't produce internal combustion engines anymore. Ford, by 2000, so this year they will produce 10 to 50%. Mercedes-Benz 15 to 25% by 2025. BMW 15 to 2025 also. Volkswagen 2050, a little bit more issues, 20 to 25. Toyota has a plan for 2050, stop selling ICE engines. I don't know, I don't have a Toyota car, but I wouldn't want to buy a Toyota car if I know that the company will stop building internal combustion engines, because if the internal combustion engines needs a part that you need to buy the manufacturer, then you don't have, what are you gonna do? You're gonna throw away your car because you don't have the piece that they used to produce. So if you guys want to buy a Toyota car, I suggest not to buy a Toyota car, because they're gonna stop selling EV, internal combustion engine. The top 10 hold. So this is what they mentioned in 2017 and 19, before the COVID crisis. Now with Tesla booming and oil companies going bankrupt, this is probably going to become even more they will probably increase their targets for electrification in their production lines. So top 10 holding global lithium ETFs, so the companies that produces lithium. So Tesla produces lithium ion batteries, Panasonic, Samsung, Enexis. The biggest one is Albemarle Corp. This was 2019. The end of 2019, Tesla Incorporation, for example, started building these gigafactories. They have I think 2 gigafactories in the US, one in California, one in Texas. They had, I think one of them in Texas is already producing. They have they're building one in Germany, they're building one in China. So Tesla is definitely going to become first place. I mean, there are other Chinese companies. Chinese are crazy, right? So they're also going to probably compete with Tesla on the production of lithium-ion batteries. So talk about costs of lithium-ion batteries. We have the cobalt is the one that they vary the most. So cost of cobalt has risen, and the cost of cobalt has a huge impact on the cost of the cells. Everyone wants to buy lithium-ion cells. Cobalt lithium cells is good, is great, is working. Everyone wants cobalt. Price of cobalt goes up. Probably they can, because of the high cost of cobalt, they can find another type of material for the anode. Sorry, not the cathode. The cathode is the important one. The cathode is the one that pulls the lithium, and the anodes is the shell, usually. So nickel also cathode. Lithium is, you have to have the lithium. You cannot go without the lithium, because lithium is great. It's very light. It's the lightest metal. Cost of lithium-ion battery reducing. For example, 2011, the cost was $917 per kilowatt hour of energy storage. Today, $135 megawatt hours, very cheap. I didn't find this in the market. By the way, I was looking for costs for battery. I couldn't find this in the market. So if I want to buy, I can't get this price, but I found a good price, and I'm going to show it to you. I'm going to do some estimates of what you can do with my battery. So if the cost of lithium doubles, for example, if doubles the cost of lithium, the cost of the battery, the whole battery will increase 5.6%. If the whole cost of cobalt doubles, you have increased 2.4%. Nickel, they put here a much higher cost, but they also increase substantially the cost of the nickel. So if you double the cost of nickel, you have 4.7%. Nickel is very expensive, and you need, the thing is that you need a lot of nickel, right? So if you go back here, you need a lot of nickel. So if the price of nickel go up, of course, the battery will become more expensive, and you need a lot of nickel. So the impact of the overall cost of the cell is high. It's not that nickel is more expensive than lithium. It's just because you need more in the battery. So comparing battery costs with offshore winds, onshore winds, PV, you still have that battery costs are much more expensive. So it's cheaper to build PV and generate electricity with this PV. So assuming that the PV only have 20% capacity factor, the battery will still, so a battery that stores energy for 4 hours, so during peak hours it generates, it would cost 3 times more expensive than the solar panels that generate electricity. Not a viable alternative yet in 2019, but as you can see, the cost is going down very quickly. So the cost is going down very quickly, but also, so this is 2005, a long time ago, but also the energy density of these batteries, lithium-ion batteries, are also increasing year by year. So this study is very interesting that says that now we are in this point, 2015, that the whole amount of lithium-ion batteries in the whole world can store 3 minutes of energy. And at this stage, the cost of electricity with this system will be $180 per megawatt hour, which is really expensive. For example, a gas power plant generates electricity in the US for of lithium increases, which this is the cumulative world capacity of batteries, and you reach a point that you have enough batteries that can store 1 day of electricity for the whole world, the cost of battery will vary from this point to this point, but in the average you have that, oh sorry, this is something, this is flow battery. Sorry. So the cost from this yellow to this blue line, so the lowest price will be $20 per megawatt hour, which is still double the price of generating gas with gas. But gas, I mean, gas is just, you take fossil fuels from the ground and you burn in the turbine, you know, it's cheap, right? So it's more expensive than gas, but twice the price. You don't have the drawbacks of gas to generation, which is with emissions, it's polluting environments and stuff. So looking at this black line, you have flow batteries. Flow batteries are cheaper for grid generation, and I'm going to go through in the next slides. This also shows the costs. I added here, but it just shows that battery cost is reducing, but not as fast as solar batteries, solar generation, because solar PV generates electricity, right? And a lot of people put money into solar, but now that batteries are actually going to be used for transport, so currently the rate of reduction in cost is lower than PV, but probably in the next 10 years the cost will reduce very quickly because there will be a lot of people buying lithium-ion battery cars. So comparing Tesla with Nissan, with other battery cars, the cost of Nissan and Tesla are the lowest. So Tesla's battery are here, Nissan batteries are here. So they found a very good balance for the cost of the car, and they started they started before in the market. I mean, Tesla has a lot of money, so they can take like 1% of the shares that Elon Musk has and buy, for example, 10 lithium mines around the world. So he has money, power, so he can lower this price much faster than the others can because he has money. But he also is a very driven CEO, has a lot of good intentions, and people like him. So then that's the reason why he has a lot of money. So these are the competitors. So the competitors range in this blue shade, green shade, Nissan, and Tesla. And the projections show that by 2020, the cost will be $100. It is $100 per megawatt hour in 2 years. That's what they say. Probably true. So this compares Tesla, Nissan, General Motors. This is showing that Nissan is more expensive, General Motors is cheaper. I'm not sure if this is true, so it's competing information. Sorry, forget about this source. It looks research. They're probably not very reliable. Forget about this slide. Lithium-ion battery costs. So lithium-ion battery costs further from today until 2030. The expectation published by EPE. So this is an EPE publication. By 2030, you have $62 per kilowatt hour, which is something like half the cost for what we have today, around half the cost we have today. So I was looking through Alibaba, so that's where I look for costs for things. Alibaba is great. And I found this container that I can buy for $200, 1 megawatt hour. So it's $200 per kilowatt hour. So $200 per kilowatt hour we can buy today in Alibaba from China. Of course, you have to pay for them to delivering this, which probably costs 10% of the cost of the battery, something like this. But it's a great battery, 2,000 cycles, probably six years using daily. And I made some cost estimates, assuming that if I have an investment cost for $200 per megawatt hour at a return rate. So the return for the investment, 8% per year. And I'm using it for 6 years, which results in a discount factor of 5.6 years. So I take this 6.5 divide by 200. So to have an idea of how much this will cost for today, in order to have the levelized costs, I assume that in 1 year, I use the battery 365 times per year. And the levelized costs, assuming that I don't buy for the energy and you have no energy losses, which you do, you have 5 to 10% energy losses because the efficiency of the battery. But a very quick calculation here, not considering the energy losses you have, that the levelized cost for energy storage is $118 per megawatt hour, which is equivalent to 650 reals per megawatt hour. So in other words, it's impossible to make this battery viable using the PLD, which is the cost of electricity in Brazil, because it only varies 520 reals per megawatt hour. Because if you buy the electricity and you sell, you don't pay for the cost of the battery, which is not good, so it's not viable. Even if you buy the cheapest, which is 40 reals per megawatt hours, and sell the most expensive, you don't pay now the cost of the battery. But there are some locations, some tariffs, some bills in locations where distribution is difficult and they have a lot of issues with peak demand. What happens is that they have tariffs with which the cost of electricity is during peak times is 120 reals per megawatt hour, and off peak is 200. And in these cases, today, this battery, it's viable. So if you have a supermarket in a region where the peak generation is 1,200 reals per megawatt hour during peak time and 200 reals per megawatt hour during off peak time, then you make money. There is also some issues with batteries, is because they create these dendrites, which is when the lithium is going through the electrolyte, they create these traces, so they destroy the electrolyte, and then the battery life reduces, the voltage reduces, the amount of current that can pass this through quickly reduces, and then you have to throw away your battery and buy a new one. These are the dendrites. It's the main cause of lithium-ion battery degradation. I think that's it really. I have several more slides which I created, but I would talk about redox flow batteries, but we don't have time because it's 6 o'clock. 5 to 6. So do you guys have any questions about lithium-ion batteries so far?
I have one question about this study of yours, of the return of this investment of Alibaba batteries that you just presented. Well, I had some similar idea that I would like to do for my final work at this course. It seems it doesn't work. Thank you then. But my question, you put 8% of return that was fixed. I mean, you have chosen 8% rate of return,
I chose
at least of
8%.
8%.
Yeah.
Okay.
Yes. It's back in the day, you could just put your money in the treasury, Brazil treasury, and get a 12% return. It would never make sense to invest because you have risk. You know, maybe you buy a battery, somebody steals your battery, or the battery explodes. You need to pay somebody to operate the battery. So but nowadays you don't have these options for very safe returns in Brazil. So 8% is very low return on investment, very low, very low. So probably no one in Brazil would invest in a project which gives you 8% of return. Only if it's within a broader picture where eventually you'll make more money or stuff like this. 8% is not enough. I put 8% just to give a reasonable levelized cost, because the main issue here is the investment cost. And if you have a high investment rate of return, you never pay for these batteries, right? So
yeah. I was looking for this idea for my final job, and then so you answered right now it is not feasible. And I also had a look at RGE company, RGE in Portuguese, about the costs, and it seems that it's really not feasible also for here where
it's feasible for locations, for distribution, for example, that they have this very different costs for between peak demand and off peak. I have seen some tariffs that in locations where distribution costs are very high, for example, in farms, locations which are very low density, these locations cost too much to increase the distribution system. So they make these tariffs with the people that, for example, want to lower their electricity bills. They buy a generator and they generate electricity with generator for 3 hours because they can then enter in these electricity tariffs, which allow you to generate electricity, buy cheap electricity during off peak, but peak load you don't consume energy, you turn on your diesel engine.
Yeah.
But I have to say something. I heard today the banks, for example, Sicredi is giving loans 5%. So they give you a loan with 5% discount, 5% return for if you want to buy solar panels. For example, if you want to buy a solar panel and put it in your house and lower your electricity bills, today you can go to the bank and they give you 6 to 5% returns, depending on your credit balance, of course. If they know that you'll pay them back. And the reason why is because they are getting money from the Banco Central from 2%. So the interest rate for money printed by the central bank today is 2%. They have the source. They buy it from 2%, and if you of course pay what they are telling you to pay, which is 5%, they make money. Of course, they have a lot of risk. For example, you can have a geada, which destroy all your solar panels. Those really big icy blocks. You're expecting to generate solar power for 20 years, but then you generate for 2 years because they're destroyed. So it's a highly risky investment. In Brazil, people can climb your roof and steal your solar panels also, so another risk.
Yeah, that's
Okay, guys, ready for questions? More questions? Did you guys like this battery lecture? I have to say, tell you that I had to learn all of this in 2 days, so it was very intense to teach you.
Yes, I like it very much. It was very nice.
Thanks. Please let me know if you have questions, and see you next week.
Thank you. See you.
Bye.
Bye.
Thank you, Julian. Bye bye.
Bye.